The universe drifts in a long and quiet night. 150 million years have passed since the great flash of the cosmic microwave background faded into darkness, leaving behind a calm and silent cosmos. There are no stars yet, no galaxies, no clusters or planets. Only a thin sea of hydrogen and helium stretching across space like a cold, tranquil mist. This is not darkness as we know it on Earth. This is a deeper, untouched darkness. A darkness that has never been pierced by starlight. The universe has expanded greatly, cooling with every passing million years. The once blinding heat of the Big Bang has stretched into a faint microwave glow. The gas temperature has fallen to just a few dozen degrees above absolute zero. Space is quiet, almost perfectly smooth, with only the faintest ripples left behind from ancient quantum fluctuations. These tiny ripples are the seeds of everything to come. Invisible structures of dark matter have already formed, shaping the cosmic landscape. They sit like vast, silent mountains made of shadow. Hydrogen drifts toward them slowly, sliding into their gravitational basins. Most of the universe remains empty and still, but in a few special regions, the gas begins to gather softly, patiently, over tens of millions of years. If you could float here, suspended between clouds of primordial gas, the silence would feel endless. There would be no color, no motion, no sound. Only the gentle pull of gravity, working quietly in the background, guiding atoms into slowly collapsing regions. This era is called the Cosmic Dark Ages, a time of waiting, a time of preparation. The hydrogen filling the universe is neutral, cool, and transparent to most forms of light, yet the universe is still dark because no objects exist to produce any light at all. The gas spreads evenly across enormous distances, occasionally forming wisps and concentrations where gravity is just strong enough to nudge atoms closer together. Over millions of years, the densest pockets begin to change. The gas inside them grows slightly warmer, slightly thicker. These pockets are still far too diffuse to form stars, but they mark the first step toward structure. The universe is beginning to move from smoothness toward complexity. Even in this vast quiet, you can sense a slow gathering of momentum, a cosmic inhalation. Something is building. As hydrogen continues to fall inward, density rises. Some regions reach a tipping point where cooling, gravity, and slow inward pressure begin to work together. Though nothing glows yet, you could imagine faint warmth developing at the heart of these clouds, hidden, invisible, but strengthening over time. This is the moment where the universe prepares to awaken. Soon, these gentle collapses will narrow into dense cores. Soon, gravity will tighten its hold. Soon, the first true structures will appear, small, fragile, yet powerful enough to change everything that follows. The great dark night of the cosmos is nearing its end. And deep within these silent clouds, the first sparks of starlight are ready to form. Gravity shapes the cosmos with infinite patience. It is the architect of structure, the sculptor of form, working on timescales that dwarf human comprehension. Unlike the other fundamental forces that govern the quantum realm or bind atoms together, gravity cannot be shielded or neutralized. Every particle possessing mass responds to its gentle but inexorable pull, and every particle contributes to the gravitational field permeating all of space. The density variations imprinted during the universe's birth have been growing steadily for 150 million years. This growth follows a simple principle that leads to profound consequences. Where matter gathers more densely, gravitational attraction strengthens. Stronger gravity pulls additional matter from surrounding regions, further increasing the density. This creates a feedback mechanism where the rich grow richer and the poor grow poorer, amplifying small differences into significant contrasts. These density enhancements exist simultaneously across a vast hierarchy of scales. The largest ripples span hundreds of millions of light years and will eventually become superclusters, the greatest structures the universe will ever construct. Medium-sized fluctuations, a few million light years across, will collapse into individual galaxies. Smaller ripples still will form star clusters, and the tiniest perturbations will give birth to individual stars. All these scales are collapsing simultaneously, nested within each other in a cosmic architecture of breathtaking complexity. Dark matter dominates the gravitational landscape. This mysterious substance comprises approximately 85% of all matter in the universe, yet it interacts with nothing except through gravitational attraction. It cannot emit, absorb, or reflect light. It passes through ordinary matter like a ghost through walls. But this very simplicity gives dark matter a crucial advantage in structure formation. Without electromagnetic interactions or internal pressure to resist collapse, dark matter can freely gather into dense concentrations, leading the way for ordinary matter to follow. The first gravitationally bound structures to emerge are dark matter halos. These roughly spherical regions mark places where dark matter has collapsed into stable configurations, no longer expanding with the universe, but held together by their own gravity. Though invisible to any conceivable telescope, these halos are substantial and real. A typical halo destined to host a small galaxy might contain 1 million solar masses of dark matter, creating a gravitational well hundreds of light years across. The drifting hydrogen begins to respond to these invisible structures. Initially, the effect is subtle. Individual atoms experience tiny deflections in their paths, velocity changes measuring just meters per second. But these small perturbations accumulate over time. The hydrogen streams gradually accelerate toward the halos, flowing along contours in space-time carved by dark matter's gravity. What begins as barely perceptible motion will eventually become a torrent of infalling gas. As hydrogen accumulates within the halos, local densities climb from cosmic averages. Regions that once contained a few atoms per cubic meter now house dozens or hundreds. By terrestrial standards, this remains an exquisite vacuum, far more tenuous than anything achievable in the finest laboratory. But by cosmic standards, these concentrations represent significant overdensities. The accumulating gas begins to exhibit collective behavior. Atoms collide with increasing frequency, and internal pressure starts to build, creating the first resistance to gravitational collapse. The geometry of collapse is not spherically symmetric. The original density fluctuations possessed slight asymmetries, and these become amplified as matter falls inward. Gas streams in faster along certain directions, creating structures stretched into filaments and compressed into sheets. This anisotropic collapse gives birth to the cosmic web, the magnificent large-scale pattern that will define the universe's architecture for billions of years. Galaxies will form where filaments intersect, like dewdrops gathering where spider silk strands meet. Turbulence awakens within the inflowing gas, where streams of hydrogen converge from different directions. They collide and generate chaotic motion. Eddies and vortices form, swirling regions where gas churns in complex patterns. This turbulence serves an important function, redistributing angular momentum throughout the collapsing cloud and preventing all matter from plunging directly toward the center. Some turbulent kinetic energy dissipates into heat through friction, providing one of the first mechanisms for converting gravitational energy into thermal energy. The behavior of gravity during this epoch differs profoundly from its role in the later universe. In a cosmos filled with stars and galaxies, gravity frequently produces rapid, violent events, supernovae that explode in hours, neutron stars that collide in seconds, black holes that merge in fractions of heartbeats. But in the universe at 150 million years, gravity operates with geological slowness. Transformations unfold over millions or tens of millions of years, changes so gradual they seem imperceptible, even though they are inexorable. Different density fluctuations collapse at different rates depending on their initial amplitude and size. The most massive perturbations, future superclusters spanning hundreds of millions of light years, will require billions of years to complete their collapse. Medium-scale ripples destined to become galaxies will take hundreds of millions of years. The smallest fluctuations that will form individual stars collapse most rapidly, yet even these require millions of years to transform from diffuse clouds into stellar objects. Temperature evolution within collapsing regions follows from basic thermodynamics. As gas falls deeper into gravitational wells, gains kinetic energy through the conversion of potential energy. This manifests as increased atomic velocities and rising temperatures. Higher temperatures generate greater pressure, which opposes further collapse. Whether a region can continue contracting depends critically on whether the gas can radiate away this thermal energy faster than compression generates it. This competition between heating and cooling will determine where and when the first stars can form. Regions that once contained a few atoms per cubic meter now house dozens or hundreds. By terrestrial standards, this remains an exquisite vacuum, far more tenuous than anything achievable in the finest laboratory. But by cosmic standards, these concentrations represent significant overdensities. The accumulating gas begins to exhibit collective behavior. Atoms collide with increasing frequency, and internal pressure starts to build, creating the first resistance to gravitational collapse. The geometry of collapse is not spherically symmetric. The original density fluctuations possessed slight asymmetries, and these become amplified as matter falls inward. Gas streams in faster along certain directions, creating structures stretched into filaments and compressed into sheets. This anisotropic collapse gives birth to the cosmic web, the magnificent large-scale pattern that will define the universe's architecture for billions of years. Galaxies will form where filaments intersect, like dewdrops gathering where spider silk strands meet. Turbulence awakens within the inflowing gas, where streams of hydrogen converge from different directions. They collide and generate chaotic motion. Eddies and vortices form, swirling regions where gas churns in complex patterns. This turbulence serves an important function, redistributing angular momentum throughout the collapsing cloud and preventing all matter from plunging directly toward the center. Some turbulent kinetic energy dissipates into heat through friction, providing one of the first mechanisms for converting gravitational energy into thermal energy. Conservation of angular momentum profoundly shapes the collapse process. Every cloud possesses some initial rotation, however slight, inherited from tidal forces during its formation. As the cloud contracts, this rotation must accelerate to conserve angular momentum, following the same principle that causes spinning ice skaters to rotate faster when they pull in their arms. Initially rotating almost imperceptibly, the clouds will eventually spin rapidly enough that centrifugal forces become significant, flattening the collapsing regions into rotating disks. The distribution of matter throughout the universe grows increasingly heterogeneous with each passing eon. The void's regions, where density falls below the cosmic average, are being systematically drained of their hydrogen. Gas flows out of voids and into overdense regions along the connecting filaments of the cosmic web. The voids expand and empty, becoming vast bubbles of near-nothingness. Meanwhile, the dense regions grow denser and more massive, accumulating material at accelerating rates. The universe is segregating itself into regions destined for structure and regions that will remain nearly empty forever. Gravity's reach extends across distances that challenge comprehension. Though gravitational force weakens with the square of distance, the sheer quantity of matter in the universe ensures that everything remains gravitationally connected to everything else. A density fluctuation in one corner of the cosmos generates gravitational effects that propagate throughout the entire universe, though they may be vanishingly small at great distances. This cosmic interconnectedness means that structure formation in one region subtly influences structure formation everywhere else. At 150 million years, the universe occupies a transitional threshold. The cosmic dark ages are drawing to a close, but the era of starlight has not yet commenced. Gravity has completed its preliminary work, gathering matter into configurations where densities are high enough that further evolution is inevitable. The stage is set, the actors are in position, but the curtain has not yet risen. The universe stands poised on the brink of transformation, waiting for the final conditions that will ignite the first stars and flood the darkness with light. For stars to be born, the primordial gas must cool. This principle governs star formation today, and governed it in the ancient universe. When gas falls into a gravitational well, compression heats it. Atoms move faster, collisions become more energetic, and temperatures rise. This heating generates internal pressure that pushes back against gravity. Without an efficient mechanism to shed this thermal energy, the gas reaches equilibrium, where pressure balances gravitational attraction and collapse halts before stars can form. In astrophysics, cooling means radiation. Atoms and molecules excited by collisions can emit photons that carry energy away from the gas. When excited electrons drop to lower energy states, they release light. If these photons can escape the cloud rather than being reabsorbed, the gas loses thermal energy, its temperature falls, pressure diminishes, and gravity can resume pulling matter into smaller volumes. The efficiency of this cooling process determines how quickly and completely gas can collapse into star-forming cores. The primordial universe presents extraordinary challenges for cooling that modern star-forming regions do not face. The gas consists almost entirely of hydrogen and helium, with essentially no heavier elements. In contemporary star formation, elements like carbon and oxygen play crucial roles as coolants. Their complex electron configurations allow them to radiate efficiently across a wide range of temperatures, facilitating rapid cooling even in relatively warm gas. But these elements do not yet exist in the early universe, having not yet been forged in stellar cores and dispersed by supernovae. Atomic hydrogen possesses a cooling mechanism, but it operates only under restrictive conditions. The single electron orbiting the proton can be excited to higher energy levels through collisions, and when it falls back to the ground state, it emits an ultraviolet photon. However, the energy required to excite these electronic transitions is substantial. Collisions must be energetic, which requires high temperatures, typically several thousand degrees or more. At the temperatures of several hundred degrees characteristic of collapsing primordial gas clouds, atomic hydrogen cooling is negligibly inefficient. Molecular hydrogen becomes the crucial coolant, enabling primordial star formation. When two hydrogen atoms bond into a molecule, the resulting structure can rotate and vibrate. These rotational and vibrational modes have much smaller energy spacing than electronic transitions, corresponding to infrared photons rather than ultraviolet. This allows molecular hydrogen to radiate at much lower temperatures. Invertoliate, a molecule rotating or vibrating at higher speeds can emit an infrared photon and drop to a lower energy even when the gas is relatively cool. Yet forming molecular hydrogen in the primordial universe is not straightforward. Two hydrogen atoms cannot simply collide and stick together to form a stable molecule. Such a two-body reaction would violate conservation laws. There is no way to simultaneously conserve energy and momentum without a third body to carry away the excess. In modern interstellar space, dust-grained surfaces provide locations where hydrogen atoms can meet, bond, and transfer excess energy to the grain. But the early universe contains no dust, no solid particles of any kind. Molecular hydrogen must form through less efficient gas phase reactions. The dominant formation pathway involves negative hydrogen ions as intermediaries. Under certain conditions, a hydrogen atom can capture a free electron to temporarily form a negative ion. When this ion subsequently collides with another neutral hydrogen atom, they can bind together into a molecule while simultaneously ejecting the extra electron, which carries away the excess energy. This process requires specific conditions and proceeds slowly, but it is the only viable pathway in the absence of dust grains. Formation rates depend strongly on gas density and the availability of free electrons. Once molecular hydrogen concentrations reach sufficient levels, cooling can begin in earnest. The molecules become excited through collisions with atoms or other molecules. They then emit infrared photons, which can escape the cloud if optical depth is not too great. The cooling rate depends on the density of molecular hydrogen and the gas temperature. Higher densities mean more frequent collisions and faster excitation, enhancing cooling rates. But if density becomes too extreme, the gas turns optically thick to infrared radiation, trapping photons and reducing cooling efficiency. The cooling process exhibits intricate self-regulation through multiple feedback mechanisms. As gas cools, its pressure decreases while gravity remains constant, allowing the cloud to contract further. Higher density enhances molecular hydrogen formation rates, which increases cooling efficiency, which permits continued collapse in a positive feedback loop. However, negative feedbacks also operate. If density grows too high, optical depth increases and cooling becomes less efficient. If temperature drops too low, the chemical reactions forming molecular hydrogen slow down, limiting coolant production. The timescale required for cooling extends across millions of years. This duration is rapid on cosmic scales, but slow compared to dynamical timescales, the time required for unchecked gravitational collapse. Cooling time essentially sets the pace of star formation in the early universe. Regions where conditions favor rapid cooling will form stars sooner. Regions where cooling proceeds slowly will remain diffuse for longer periods, delaying their transformation into stellar nurseries. Thermal stratification develops naturally within collapsing clouds. Outer regions, where densities remain relatively low, cool slowly and stay warmer. They contain primarily atomic hydrogen with little molecular formation. Inner regions, where densities climb higher, cool more efficiently. Molecular hydrogen becomes abundant there, and temperatures drop substantially. This creates a temperature gradient from warm, diffuse exteriors to cold, dense cores. The coldest, densest regions at cloud centers will become the sites where protostars eventually form. The absence of metal cooling makes primordial star formation fundamentally different from modern processes. In the present-day universe, collapsing molecular clouds can cool to temperatures as low as 10 degrees above absolute zero through radiation from trace amounts of carbon and oxygen. This extraordinarily efficient cooling allows fragmentation into small masses, enabling the formation of stars like our Sun or smaller. Primordial gas, restricted to molecular hydrogen cooling, typically cannot cool below a few hundred degrees. The warmer minimum temperatures require higher densities to achieve comparable pressures, biasing the first stars toward higher masses. The cosmic microwave background radiation imposes a temperature floor on the cooling process. At 150 million years, this relic radiation has cooled to approximately 20 degrees above absolute zero. The universe is bathed in this faint microwave glow uniformly. If collapsing gas cools below this background temperature, the cosmic radiation actually heats it back up rather than allowing further cooling. This sets an absolute lower limit on gas temperature. Matter cannot become colder than its surroundings without an external energy sink. Primordial helium, though abundant, contributes negligibly to cooling. Helium atoms have even simpler electronic structures than hydrogen. The energy required to excite helium's electron states is very large, corresponding to high-energy ultraviolet photons. At the temperatures relevant for primordial star formation, Helium remains in its ground state, neither absorbing nor emitting radiation. It comprises about 25% of the gas mass, but acts as a passive component, swept along in the collapse without influencing thermal evolution. Turbulent motions within collapsing clouds can either enhance or inhibit cooling, depending on circumstances. Turbulence generates shock waves where gas compresses suddenly. These shocks heat the gas, but they also increase density, which can accelerate molecular hydrogen formation. Whether turbulence aids or hinders cooling depends on the balance between shock heating and enhanced chemical reactions. Additionally, turbulence prevents gas from settling smoothly, potentially disrupting organized collapse and prolonging the time required to reach star-forming densities. The transition from warm diffuse clouds to cold dense protostellar cores is gradual rather than sudden. There is no discrete moment when cooling succeeds. Instead, different regions cool at different rates depending on their local conditions. Some fortunate regions achieve efficient cooling within just a few million years, rapidly collapsing into dense cores. Others require tens of millions of years. Still others never cool efficiently enough, remaining diffuse indefinitely or being dispersed by external influences before they can collapse. Understanding this cooling process requires careful energy accounting. For collapse to proceed, the rate at which gravity converts potential energy to thermal energy must be exceeded by the rate at which radiation carries thermal energy away. If these rates balance, the cloud reaches equilibrium and collapse stalls. Only when cooling dominates can gravity win the competition, driving the cloud toward ever higher densities. Molecular hydrogen, despite being a relatively simple molecule, is the key that tips this balance. It is the substance that cools the primordial gas sufficiently for the first stars to form, breaking the universe free from its long darkness. The waiting ends. After millions of years of gradual accumulation, patient cooling, and slow contraction, collapse accelerates dramatically in the densest cores. Gravity, having won its long competition with pressure, now pulls matter inward with growing urgency. The hydrogen and helium that drifted lazily through space for eons now stream toward cloud centers at velocities measuring hundreds of meters per second. These cores are becoming the birthplaces of the first protostars. A protostar represents a star in formation, an intermediate stage between a diffuse cloud and a nuclear burning star. It has not yet achieved the temperatures and densities necessary to fuse hydrogen nuclei, but it has already become a distinct object, a gravitationally bound concentration of gas, contracting and heating, growing more massive with each passing moment. The appearance of these first protostars marks a profound transition from the era of passive waiting to an era of active transformation. Collapse does not proceed uniformly from all directions. The cloud possesses residual angular momentum, a slow rotation inherited from tidal torques during its formation. This rotation was imperceptible when the cloud was large and diffuse, but conservation of angular momentum demands that rotation accelerate as the cloud contracts. Gas falling inward along the rotation axis can reach the center relatively easily, But gas approaching from equatorial directions finds its inward motion increasingly opposed by centrifugal forces. Matter that cannot reach the center directly settles into a rotating disk encircling the growing protostar. This disk is vast by stellar standards, often extending thousands of astronomical units, thousands of times the Earth's sun distance. Rotation flattens the disk into a thin structure, much wider than it is thick. Within this disk, gas spirals slowly inward, gradually shedding angular momentum through turbulent friction and magnetic field interactions, working its way toward the protostar at the hub. The disk actively channels matter onto the central object. Gas in the disk is not static but dynamic, orbiting the protostar while simultaneously drifting inward. As gas moves towards smaller orbits, gravitational potential energy converts to kinetic energy, heating the material. The inner disk regions glow hotly in infrared light, warmed by friction as gas spirals inward. The disk is not merely a storage reservoir, it is a conduit, feeding the protostar and governing how rapidly it can grow. The protostar itself grows with remarkable speed. Beginning as a small condensation with minimal mass, it swells rapidly as material rains down from the disk and directly from the still collapsing cloud envelope. In modern star formation, typical accretion rates measure about 1/1,000,000th of a solar mass per year. The first protostars accrete far more rapidly, perhaps 1/10,000th of a solar mass annually, or even faster. These high accretion rates stem from the warmer gas temperatures and more massive initial clouds characteristic of the primordial universe. Internal temperatures climb steadily as the protostar contracts. The weight of overlying gas compresses the core, and this compression generates heat through the conversion of gravitational potential energy. Core temperatures reach millions of degrees, hot enough to fully ionize the gas. Electrons are stripped from atomic nuclei, creating a plasma of freely moving particles. Yet even at several million degrees, conditions remain insufficient for hydrogen fusion, which requires core temperatures exceeding 10 million degrees. The protostar shines brightly despite lacking nuclear reactions. Its luminosity comes entirely from gravitational contraction. As the protostar shrinks, half of the liberated gravitational energy heats the interior, while the other half radiates into space, a consequence of the virial theorem governing gravitationally bound systems. This contraction-powered luminosity can be substantial. A massive protostar might shine with thousands or tens of thousands of times the sun's luminosity, all generated by the simple act of shrinking under its own weight. Infrared emission dominates the protostar's spectrum. The stellar surface, heated to thousands of degrees by the energy released from contraction, glows primarily in infrared wavelengths. The surrounding disk also contributes substantial infrared radiation, particularly from its hot inner regions, where temperatures soar highest. Were an observer positioned nearby, they would see a brilliant infrared source, glowing disk with a luminous central star, all embedded within a faint envelope of still in falling gas visible as a diffuse glow. Jets and outflows frequently accompany protostellar birth. Not all accreting material reaches the stellar surface. Some fraction is redirected outward along the rotation axis, creating high-velocity outflows that stream away from the protostar at speeds sometimes exceeding thousands of kilometers per second. These jets are powered by complex interactions involving magnetic fields threading through the disk and radiation pressure from the protostar itself. The outflows collide with surrounding gas, creating shocks and carving cavities that shape the larger cloud. The timescale for protostellar assembly is brief by cosmic measures. From the moment the core begins its final rapid collapse to the moment the protostar achieves its full pre-fusion mass might span only a few 100,000 years. This represents a blink compared to the millions of years required for initial cooling and slow contraction. Once gravity overwhelms pressure and collapse begins in earnest, events unfold rapidly. The universe shifts from a mode of slow preparation to quick action. The first protostars differ from their modern counterparts in critical ways. They are typically much more massive, tens to hundreds of solar masses rather than solar mass or smaller. They form from chemically pristine gas, lacking the dust grains and heavy elements that facilitate efficient cooling in contemporary star formation. They appear in isolation or in small groups, rather than the large clusters typical of modern star birth. These differences will profoundly shape the properties and fates of the first generation of stars. Fragmentation, the process by which collapsing clouds break into multiple pieces, each forming a separate star, is suppressed in primordial star formation. Modern molecular clouds cool so efficiently that they fragment extensively, which is why most stars today are born in clusters alongside siblings. Primordial clouds, cooled only by molecular hydrogen, fragment much less readily. The gas remains warmer, pressure stays higher, and the clouds resist breaking apart. Consequently, primordial clouds often form only one or a few stars rather than large stellar populations, and these stars are born in relative isolation. The final mass achieved by each protostar depends on the competition between accretion and feedback. As long as gas continues falling onto the protostar, its mass increases. But the growing protostar also radiates energy, and this radiation heats the surrounding gas, raising its pressure and potentially halting infall. Eventually, the protostar becomes luminous enough that its radiation prevents further accretion by dispersing or heating the reservoir of infalling material. This feedback mechanism determines where accretion stops and sets the final stellar mass. Internal structure within a protostar is relatively straightforward. A hot, dense core occupies the center, where temperatures and pressures are greatest. This core is surrounded by an envelope of gas still falling inward. No sharp boundary separates these regions instead. Temperature and density decline gradually from the hot, dense core to the cooler, diffuse envelope. Nuclear fusion will eventually ignite in the core, but that ignition awaits slightly higher temperatures. For now, the protostar continues contracting, heating and growing. Angular momentum distribution shapes both protostar and disk. The initial rotation of the collapsing cloud must be conserved throughout the process. But all that angular momentum cannot end up in the protostar itself. If it did, the protostar would spin so rapidly that centrifugal forces would tear it apart. Instead, most angular momentum is stored in the surrounding disk and carried away by outflows. This allows the protostar to accrete substantial mass without spinning itself to destruction. The formation of these first protostars constitutes a cosmic watershed. For the first time since the Big Bang itself, The universe contains objects actively concentrating energy and matter into compact volumes. After 150 million years of expansion and dilution, the cosmos now hosts pockets where density increases rather than decreases. These protostars are precursors to the universe's first sources of sustained light. The next transformation, ignition of nuclear fusion, will flood the darkness with radiance and forever change the nature of the cosmos. Deep within the protostar's core, temperature crosses a critical threshold. Millions of years of contraction have compressed the core to extraordinary densities and heated it to unimaginable temperatures. The thermometer climbs past 1 million degrees, then 5 million, then approaches 10 million. At this crucial temperature, hydrogen nuclei bear protons, move fast enough to overcome the electromagnetic repulsion that normally keeps them apart. When they collide, they fuse. Nuclear fusion ignites for the first time in hundreds of millions of years. The reaction is elegantly simple, yet cosmically profound. 4 hydrogen nuclei combine through a series of steps to form one helium nucleus. But the helium weighs slightly less than the 4 original protons. That tiny mass difference, following Einstein's famous equation relating mass and energy, transforms into tremendous energy. A star is born. The energy emerges primarily as gamma-ray photons, the highest energy form of light. These gamma rays are created in the core where fusion occurs, and they begin a long journey outward toward the stellar surface. But the star is extraordinarily dense, and photons cannot travel far before being absorbed and emitted by the surrounding plasma. Each photon scatters countless times, gradually diffusing outward in a random walk that can take thousands of years. When photons finally emerge from the surface, they carry the star's light into the waiting darkness. Fusion stabilizes the star's structure. Before fusion begins, the protostar's structure is in flux, continuously contracting as it seeks equilibrium. But fusion provides a stable, long-term energy source far more powerful than gravitational contraction. The outward pressure generated by the intense heat of nuclear burning exactly balances the inward crush of gravity. The star achieves hydrostatic equilibrium, a steady state where it neither expands nor contracts. It will maintain this balance for as long as fuel remains in the core. These first stars are massive giants. While modern stars span an enormous range from less than 1/10 to perhaps 100 times the Sun's mass, the first stars typically fall between 30 and 300 solar masses. This large mass carries profound consequences. Massive stars have much hotter cores than lower mass stars, which dramatically accelerates nuclear reaction rates. They consume fuel voraciously, burning through their hydrogen reserves far more rapidly than smaller stars. Astronomers designate these first stars population 3. This naming reflects stellar classification by chemical composition. Population I stars like our Sun are metal-rich, containing substantial amounts of elements heavier than helium. Population Natus 1000 globular clusters and galactic halos are metal-poor but not metal-free. Population of stars entirely hypothetical, since none have ever been directly observed, represent the first-generation stars formed from primordial gas containing no metals whatsoever, only hydrogen and helium from the Big Bang. Surface temperatures of massive population the third, stars reach extreme values, often exceeding 50,000 degrees Kelvin. This far surpasses the Sun's surface temperature of approximately 6,000 degrees. At such tremendous temperatures, the stars emit most of their radiation in the ultraviolet portion of the spectrum. Were it possible to observe a population the third, it would appear intensely brilliant light, a pine of the such brilliant light that it viewed directly even from distances of many light years. Luminosity reaches staggering levels. A typical massive population third star might outshine our Sun by a factor of 1,000,000 or more. This extraordinary brightness stems directly from the high mass. Greater mass means higher core temperatures, which drive faster fusion reactions, which generate more energy. The star is a nuclear furnace operating at maximum capacity, converting mass to energy at rates that dwarf anything occurring in the modern universe's more sedate stellar populations. Internal structure differs markedly from lower mass stars. In stars like the Sun, energy transport from core to surface occurs through radiation in the inner regions and convection in the outer envelope. Massive stars exhibit the opposite pattern, convective cores and radiative outer layers. The steep temperature gradient in massive stellar cores drives vigorous convection, churning the core material and mixing fresh hydrogen fuel into the nuclear burning region, while redistributing the helium fusion products throughout the core. The lifetime of these stellar behemoths is extraordinarily brief. A star with 100 solar masses might survive only 2 to 3 million years before exhausting its fuel. This represents less than 1,000th of the Sun's 10 billion year lifetime. The reason is straightforward. Although massive stars possess more fuel, they consume it at rates that scale far more steeply than their mass. Fusion rates in stellar cores scale roughly with the fourth power of stellar mass, vastly outpacing the linear increase in available hydrogen. Radiation pressure becomes significant in extremely massive stars. Photons carry momentum, and when absorbed or scattered by matter, they exert outward force. In highly luminous stars, radiation pressure can rival or exceed gravitational pressure. This imposes an upper limit on stellar mass called the Eddington limit, typically around a few hundred solar masses. Stars more massive than this critical value would blow themselves apart, with radiation pressure overwhelming gravity and expelling the outer layers. Powerful stellar winds stream from these massive stars. Even though the stars maintain overall stability, their intense radiation heats outer atmospheric layers until gas escapes into space. This stellar wind carries mass and energy outward at velocities reaching thousands of kilometers per second. The wind creates a bubble of hot gas around the star, excavating a cavity in the surrounding primordial hydrogen cloud and depositing energy and momentum into the interstellar medium. The ultraviolet radiation pouring from these stars produces even more dramatic effects. Photons, carrying more than 13.6 electron volts, possess sufficient energy to ionize hydrogen atoms, stripping away electrons. Population 3 stars generate prodigious floods of these ionizing photons. The radiation streams outward at light speed, encountering the neutral hydrogen pervading the universe. But fusion provides a stable, long-term energy source far more powerful than gravitational contraction. The outward pressure generated by the intense heat of nuclear burning exactly balances the inward crush of gravity. The star achieves hydrostatic equilibrium, a steady state where it neither expands nor contracts. It will maintain this balance for as long as fuel remains in the core. These first stars are massive giants. While modern stars span an enormous range from less than 1/10 to perhaps 100 times the Sun's mass, the first stars typically fall between 30 and 300 solar masses. This large mass carries profound consequences. Massive stars have much hotter cores than lower mass stars, which dramatically accelerates nuclear reaction rates. They consume fuel voraciously, burning through their hydrogen reserves far more rapidly than smaller stars. Astronomers designate these first stars population 3. This naming reflects stellar classification by chemical composition. Population I stars like our Sun are metal-rich, containing substantial amounts of elements heavier than helium. Population Natus 1000 globular clusters and galactic halos are metal-poor but not metal-free. Population of stars entirely hypothetical, since none have ever been directly observed, represent the first-generation stars formed from primordial gas containing no metals whatsoever, only hydrogen and helium from the Big Bang. Surface temperatures of massive population III stars reach extreme values, often exceeding 50,000 degrees Kelvin. This far surpasses the Sun's surface temperature of approximately 6,000 degrees. For the first time since the universe became transparent 380,000 years after the Big Bang, concentrated sources of light exist. Not the diffuse glow of the cosmic microwave background, but brilliant starlight emanating from point sources. The universe is no longer dark. It blazes with the blue-white radiance of massive young stars, illuminating the cosmic fog and beginning the long process of transformation that will give the universe its modern character. Ultraviolet photons pour outward from the first stars like floods from broken dams. Each massive population, the third star, is an ultraviolet powerhouse, emitting vast quantities of photons energetic enough to ionize hydrogen atoms. These photons race outward at light speed, penetrating the neutral hydrogen gas that fills the universe. When an ionizing photon encounters a hydrogen atom, it strips away the electron, transforming the atom from neutral to ionized in an instant. Ionization fundamentally alters hydrogen's properties. A neutral hydrogen atom consists of a proton nucleus orbited by an electron, bound together by electromagnetic attraction. This bound system can absorb photons of specific wavelengths corresponding to electronic transitions between energy levels. These absorption properties make neutral hydrogen opaque to certain wavelengths. An ionized hydrogen atom, by contrast, is simply a bare proton with no electron. Unable to absorb photons through electronic transitions, ionized hydrogen is effectively transparent to most radiation. An expanding bubble of ionized gas forms around each newborn star. Initially small, perhaps only a few light years in radius, the bubble grows rapidly as the star continues pouring out ionizing photons. Every photon that escapes contributes to bubble expansion, The bubble's edge, where ionized gas transitions to neutral, is called an ionization front. This front is thin, often only light years thick, marking the boundary between two fundamentally different states of matter. Ionized gas is dramatically hotter than neutral gas. When an ultraviolet photon ionizes a hydrogen atom, the freed electron typically receives excess kinetic energy beyond the 13.6 electron volts needed to break the bond. This excess energy thermalizes through collisions, heating the gas to approximately 10,000 degrees Kelvin. At this temperature, hydrogen exists as a fully ionized plasma, sea of free electrons and protons. The elevated temperature increases gas pressure, causing the ionized region to expand beyond what photoionization alone would produce. When multiple stars form in proximity, their ionization bubbles eventually meet and merge. If two stars are close enough, their expanding spheres of ionized gas overlap, creating a doubly ionized region exposed to radiation from both sources. The neutral gas separating the bubbles is consumed. The ionization fronts meet and annihilate, and the bubbles coalesce into a single larger bubble. This merging process is fundamental to reionization. Individual bubbles must combine to eventually fill the universe. The early stages of reionization are highly inhomogeneous and chaotic. Stars do not form uniformly across all space. They appear first in the densest regions where gas has cooled and collapsed most rapidly. These regions become ionized islands embedded in a neutral ocean. The vast voids between dense regions remain neutral for much longer. The universe, during early reionization, resembles a patchwork, with ionized regions concentrated where structure has formed earliest and neutral gas, dominating the underdense voids. Neutral hydrogen's opacity to ultraviolet radiation limits how far ionizing photons can penetrate. An ionizing photon traveling through neutral gas will be absorbed after ionizing only one or a few atoms. This short, mean-free path restricts each star's sphere of influence. A single star can ionize only its immediate vicinity, typically a few tens to perhaps a few hundred light years. Beyond that distance, the neutral gas is too dense and photons are absorbed before penetrating further. Gas density strongly modulates the reionization rate. In denser regions, numerous hydrogen atoms pack into each cubic meter, so ionizing photons are quickly absorbed. Each photon ionizes only one atom before being consumed, requiring many photons to ionize dense gas. Bubbles grow slowly in high-density environments. In underdense regions, atoms are more widely scattered. Each photon can travel farther before encountering an atom to ionize, allowing bubbles to expand more rapidly. Reionization thus proceeds faster in voids than in dense regions. Recombination opposes and complicates reionization. An ionized hydrogen atom does not remain ionized indefinitely. Free protons and electrons can recombine, reforming neutral atoms. This recombination occurs most frequently in dense gas, where particles collide often. For an ionized bubble to persist, the star must emit ionizing photons at a rate sufficient to keep pace with recombination. If the star dies or its ionizing output drops, the bubble will gradually shrink as recombination converts ionized gas back to neutral. The first stars are sufficiently powerful to overcome recombination locally. Even in moderately dense gas, the intense ultraviolet flux from a massive population 3-star ionizes a substantial volume and maintains ionization, despite ongoing recombination. However, as the bubble expands, radiation spreads over larger surface area, diluting the photon flux. Eventually, bubbles reach an equilibrium size where ionization rate matches recombination rate, and further growth stalls unless additional stars form to provide more ionizing photons. The escape fraction, the percentage of ionizing photons that escape into the intergalactic medium critically determines reionization efficiency. Not all ionizing photons generated in stellar cores reach the intergalactic medium. Some are absorbed by gas within the star itself or in the immediate circumstellar environment. For the first stars, escape fractions are thought to be high, perhaps 50% or greater, because they form in relatively isolated halos without extensive surrounding dense gas. This high escape fraction makes population the third stars particularly efficient agents of reionization. As reionization advances, the universe gradually becomes more transparent. Photons that would have been quickly absorbed by neutral hydrogen now traverse long distances through ionized gas without hindrance. This increasing transparency has profound observational consequences. Early in reionization, the universe appears opaque beyond relatively short distances. Later, as ionized regions dominate, observers can see much farther. When reionization completes, the universe becomes transparent to ultraviolet radiation, as it remains today. The topology of reionization exhibits an inside-out character. The first ionized regions appear in overdense areas where the first stars form relatively compact regions, often only a few million light-years across. As star formation continues in these regions, bubbles grow and merge. Meanwhile, the immense voids between these dense regions remain neutral much longer. Over time, ionized bubbles expand from dense regions into voids, pushing neutral gas into ever smaller pockets. The last regions to ionize are the least dense voids, far removed from any star-forming regions. Reionization unfolds over an extended period. It begins when the first stars ignite, perhaps 150 to 200 million years after the Big Bang. But completion requires several hundred million additional years, lasting until enough stars have formed to produce overlapping ionized bubbles, filling the entire universe. At 200 million years, perhaps only a few % of hydrogen is ionized. By 500 million years, the majority has been ionized, though pockets of neutral gas persist. Full completion may not occur until 700 to 800 million years post-Big Bang. The thermal structure of intergalactic gas grows complex during reionization, mirroring the ionization structure. Ionized gas is hot at 10,000 degrees, while neutral gas remains cold at a few hundred degrees. This creates a thermal patchwork, warm ionized bubbles embedded in cool neutral regions. When ionization fronts sweep through previously neutral gas, they heat it suddenly and dramatically. Behind the front, gas slowly cools through radiation, though it remains far warmer than the pre-ionization state. The first stars alone cannot complete reionization. Though powerful ultraviolet sources, they are also rare. Simply too few population of thirds stars exist to ionize the entire universe. Later stellar generations smaller, more numerous population second stars, forming in enriched gas likely, contribute substantially to finishing reionization. Early galaxies, containing many stars working collectively, probably drive reionization in its later phases. The first stars ignite the process, but galaxies complete it. Evidence for reionization comes from observing distant quasars. When astronomers study quasars at high redshift, corresponding to times before reionization completed, their spectra show strong absorption caused by neutral hydrogen along the line of sight. This absorption feature, the Gunn-Peterson trough, indicates substantial neutral hydrogen existed. Quasars at lower redshift, corresponding to post-reionization times, show much weaker absorption, demonstrating that most hydrogen has been ionized. The transition between these regimes marks reionization's end. Reionization represents one of the universe's final major phase transitions. After this transformation, the intergalactic medium will remain ionized for billions of years, maintained by ongoing star formation and active galactic nuclei. The universe will never again be filled with neutral hydrogen as it was during the Dark Ages. The first stars have permanently altered the cosmos's state, initiating a transformation that propagates across space and time, reshaping the universe from an opaque fog into the transparent expanse we observe today. The first stars are fleeting. Their immense masses guarantee brief lives measured in mere millions of years. After this cosmic instant of shining, hydrogen fuel in their cores becomes exhausted. Nuclear fusion reactions slow, then cease entirely. Without fusion energy to generate outward pressure, nothing remains to support the star against its own gravity. The core begins to collapse. Core collapse proceeds with terrifying rapidity. Without pressure support, material plunges inward at a significant fraction of light speed. The core, composed of helium and heavier elements synthesized during the star's life, implodes catastrophically. In less than 1 second, it shrinks from thousands of kilometers in diameter to a mere few tens of kilometers. Density soars to unimaginable values as protons and electrons are crushed together, merging to form neutrons. The core transforms into a neutron star, or if sufficiently massive, collapses even further into a black hole. The star's outer layers, suddenly unsupported, begin falling inward as well. But when this infalling material strikes the nascent neutron star or encounters the outward streaming flood of neutrinos released during core collapse, it rebounds violently. A powerful shockwave forms and propagates outward, driving through the star's envelope. The star explodes in a core collapse supernova, ejecting most of its mass into space at velocities exceeding 10,000 kilometers per second. The explosion blazes with astonishing brilliance. For several weeks, a single supernova outshines entire galaxies containing billions of stars. This luminosity is powered by radioactive decay of isotopes synthesized during the explosion, primarily nickel-56, which decays through cobalt-56 to stable iron-56. Each radioactive decay releases gamma rays that thermalize in the expanding ejector, producing visible light. Peak brightness is reached a few weeks after the explosion, followed by gradual fading over months as radioactive material depletes. Energy release during a supernova defies easy comprehension. The explosion liberates approximately 10 to the 51st ergs, roughly equivalent to the Sun's total energy output over its entire 10 billion year lifetime, released in mere seconds. Most of this stupendous energy is carried away by neutrinos, ghostly particles that interact so weakly with matter that they escape directly from the collapsing core and stream into space at light speed. Yet even the small fraction of energy channeled into the explosion and photons suffices to make supernovae visible across cosmic distances. Supernovae disperse heavy elements throughout space. During its lifetime, the star has fused hydrogen into helium, helium into carbon and oxygen, then continued fusion to produce neon, magnesium, silicon, sulfur, and eventually iron. Before explosion, the stellar interior was stratified like an onion-like elements in outer layers, progressively heavier elements toward the center, with an iron core at the very center. The supernova blast wave rips through these layers, ejecting them into the surrounding medium. This process explains the origin of heavy elements in the universe. Carbon, oxygen, nitrogen, silicon, iron. None of these elements formed during the Big Bang. The extreme conditions of the first few minutes after creation allowed synthesis only of the lightest elements. Everything heavier must be forged in stellar interiors and supernovae. The first supernovae are the universe's first heavy element factories, the cosmic forges where the building blocks of planets and eventually life are created. The explosion itself synthesizes additional elements through explosive nucleosynthesis. During the supernova, conditions become so extreme that nuclear reactions impossible in normal stellar burning occur. Elements heavier than iron, which consume rather than release energy when formed by fusion, are synthesized through rapid neutron capture processes. Neutrons released during core collapse are captured by atomic nuclei, building progressively heavier isotopes. This R process is responsible for roughly half of all elements heavier than iron, including precious metals like gold and platinum. The supernova ejecta expand into surrounding gas as a rapidly moving shell. This shell sweeps up ambient hydrogen and helium, mixing the stellar debris with primordial material. The shell is intensely hot, heated to millions of degrees by the passage of the shock wave, and glows brightly in X-rays. Over thousands to millions of years, the shell decelerates as it accumulates more mass and radiates energy. Eventually, the ejecta merge with the interstellar medium, dispersing heavy elements across a large volume. Chemical enrichment from the first supernovae is spatially inhomogeneous. Each supernova enriches only a localized region initially, perhaps a few hundred light years in radius. The early universe is chemically patchy, with pockets of enriched gas surrounded by vast expanses of pristine primordial material. Turbulence and galactic-scale gas flows will gradually mix enriched gas with surrounding medium, but this mixing is slow and incomplete. Some regions remain metal poor for extended periods, while others receive early enrichment. The presence of metals, even in trace amounts, transforms conditions for subsequent star formation. Metals are extraordinarily efficient coolants. Carbon and oxygen atoms possess complex electron structures, enabling them to radiate energy at much lower temperatures than molecular hydrogen. Gas containing even tiny metal fractions, as small as 1/10,000th of solar metallicity, cools far more efficiently than pristine gas. Enhanced cooling allows gas to fragment into smaller clumps, enabling formation of lower mass stars. This metal enrichment drives the transition from population to third, bipollution second, seventh stars. Once gas has been contaminated with even trace heavy elements, conditions favoring massive isolated stars disappear. Instead, stars begin forming in clusters spanning wide mass ranges. The characteristic stellar mass drops dramatically from hundreds of solar masses to approximately solar mass. This transition unfolds gradually across tens or hundreds of millions of years as supernovae progressively enrich increasing volumes of intergalactic gas. Supernovae also produce feedback effects on their immediate environment. Explosions can compress nearby gas clouds, triggering new star formation episodes through shock-induced collapse. Alternatively, explosions can disperse clouds, blowing away material that would have formed stars and quenching star formation. The net effect varies case by case depending on gas density, explosion energy, and magnetic field strength. Supernovae simultaneously stimulate and suppress star formation in complex, context-dependent ways. Some extremely massive first stars may die through different mechanisms. Stars exceeding approximately 250 solar masses may undergo pair instability supernovae rather than conventional core collapse. In these stars' ultra-hot cores, gamma-ray photons become so energetic that they spontaneously create electron-positron pairs. This pair production removes energy from the core, causing contraction and runaway heating. If this process becomes unstable, the entire star can explode without leaving any remnant, no neutron star or black hole, just complete disruption. Pair instability supernovae are even more energetic than conventional supernovae, releasing up to 100 times more energy and synthesizing much greater quantities of heavy elements. However, they are correspondingly rarer, requiring the most massive first-generation stars. Most population 3 stars produce conventional core collapse supernovae, leaving behind neutron stars or black holes. The compact remnants of first supernovae seed future black hole populations. If the progenitor star exceeds approximately 40 solar masses, core collapse may proceed directly to black hole formation without any explosion. The star simply disappears behind an event horizon, leaving a black hole with tens of solar masses. These are the seeds that will eventually grow through accretion and mergers into the supermassive black holes inhabiting galaxy centers billions of years later. The chemical legacy of first supernovae is permanent and pervasive. Once created and dispersed, heavy elements persist in the universe indefinitely. They incorporate into subsequent stellar generations, into planetary systems, and ultimately into living organisms. Every carbon atom in your body, every oxygen molecule you breathe, was created in a star and dispersed by a supernova. The first supernovae initiated this chemical enrichment, beginning the long process that makes complex chemistry and eventually life possible. This explosion is not an ending, it is a transformation that enriches the cosmos forever. The universe organizes itself into increasingly grand structures. The first stars appeared in isolated dark matter halos, burned brilliantly, but briefly, and exploded as supernovae. Yet the halos themselves are not static. They are embedded in the cosmic web, falling toward one another under gravity's inexorable attraction. When halos collide and merge, their stars and gas come together. The first galaxies are born from these mergers. A galaxy transcends being merely a collection of stars. It is a gravitationally bound system, a region where matter has collapsed sufficiently that it will remain together indefinitely, no longer participating in cosmic expansion. The first galaxies are modest by modern standards, containing perhaps only a few million stars compared to hundreds of billions in massive spiral galaxies. Yet they are distinct entities, coherent structures that represent a new level of cosmic organization. Galaxy formation begins with dark matter halo mergers. Two halos, each containing gas, and perhaps a few first-generation stars, fall toward each other along cosmic web filaments. The merger is not a solid collision, but an interpenetration. Dark matter particles pass through each other, interacting only gravitationally. Gas clouds similarly pass through, though gas does experience collisional shocks. Over time, the two halos settle into a single larger structure, their dark matter merged, their gas clouds combined, their stars intermingled. The gas in merging systems is not smooth but clumpy and filamentary, threaded with structures left over from first-generation star formation. As halos merge, gas streams collide violently, creating powerful shocks that compress and heat the material. These compression regions can trigger intense star formation bursts. Gas previously too diffused to collapse is suddenly squeezed to high densities, initiating rapid stellar birth. The newly formed galaxy lights up as massive young stars ignite throughout its volume. Early galaxies are chaotic and irregular. There are no elegant spiral arms, no smooth elliptical profiles. Instead, stellar and gas distributions are clumpy and asymmetric. Star formation occurs in concentrated bursts within dense knots where gas has been compressed by mergers or gravitational instabilities. Between these bright knots, the galaxy is sparser, filled with diffuse gas and scattered field stars. The overall appearance is turbulent and disordered, more resembling a collection of star clusters than a coherent galaxy. Stellar populations in first galaxies are diverse and age stratified. Some massive populations of their stars may still be burning, though most have already exploded. Second-generation population 2-8 stars, formed from gas enriched by earlier supernovae, dominate the stellar light. These stars are smaller and longer-lived than their population the three predecessors. The galaxy's chemical composition is therefore stratified, with ancient metal-free stars coexisting with younger, slightly enriched stars in a complex multi-generation population. Dark matter provides the gravitational framework holding galaxies together. Visible stars and gas comprise only a small fraction of total galactic mass, perhaps 15%. The remaining 85% is dark matter, distributed in an extended halo enveloping the visible galaxy. This dark matter halo extends much farther than the stellar distribution, often 10 times more. Dark matter's gravity prevents stars from dispersing despite their random motions, binding the galaxy into a stable system. First galaxies are building blocks in a hierarchical assembly process. In the now standard paradigm of galaxy formation, small structures form first, then merge to create progressively larger structures. First galaxies are the smallest units in this hierarchy. Over cosmic time, they will collide with other dwarf galaxies, merging into larger systems. These, in turn, will merge with others, eventually building the giant galaxies observed in the modern universe. Today's galaxies are descendants, amalgamations of countless first galaxies. Star formation rates in first galaxies are extraordinarily high by modern standards. Present-day galaxies typically form a few solar masses of new stars per year. First galaxies, fed by cold gas, streams flowing along cosmic web filaments and driven by frequent merger-induced starbursts, achieve rates of tens to hundreds of solar masses annually. This intense star formation produces brilliant ultraviolet emission. Those small, first galaxies are extraordinarily luminous, blazing with light from millions of young, hot, massive stars. Gas accretion from the cosmic web fuels galaxy growth. The universe's large-scale structure forms a web of filaments with galaxies at nodes where filaments intersect. Cold gas flows along these filaments, channeled by gravity into dark matter halos. This steady gas supply is crucial for sustained star formation. As long as cold streams continue flowing, the galaxy can keep forming stars. If streams shut off, perhaps due to feedback, heating, or halo growth, star formation will eventually cease. Stellar and supernova feedback regulates galaxy evolution. Stars inject energy into surrounding gas through radiation, stellar winds, and supernova explosions. This energy heats gas, increasing pressure and potentially expelling it from the galaxy entirely. Galactic scale outflows of hot gas are ubiquitous in young star-forming galaxies. These outflows carry away mass, metals, and energy, limiting how many stars can form and enriching the intergalactic medium with heavy elements. First galaxies are socially connected, rarely existing in true isolation. They typically appear in small groups or loose clusters, multiple galaxies inhabiting the same large-scale dark matter structure. These galaxies orbit one another, interacting gravitationally and occasionally merging. This clustering is a natural consequence of hierarchical structure formation. Overdense regions on large scales contain many smaller overdensities, each potentially forming a galaxy. These proto-galaxies then interact within their shared environment. Galaxy shapes are irregular and asymmetric. Without time to settle into equilibrium or strong rotation to enforce symmetry, first galaxies lack the organized structures of spiral or elliptical galaxies. They are lumpy and constantly changing as new stars form in bursts and old stars explode. Some may show hints of rotation, with gas and stars orbiting a common center, but rotational structure is disordered and not yet organized into distinct features like spiral arms or rotating disks. Gas dynamics are dominated by supersonic turbulence. Gravitational infill, supernova explosions, and merger shocks drive chaotic motions that prevent gas from settling into smooth distributions. This turbulence both helps and hinders star formation. Turbulent compression can create dense regions where stars form, But turbulence can also disrupt forming stellar embryos before they fully develop. The result is that star formation proceeds in episodic bursts rather than continuously, giving first galaxies their characteristic irregular appearance. Metallicity rises steadily over time within these galaxies. Each stellar generation produces heavy elements dispersed by supernovae. These metals are incorporated into the next generation, progressively enriching the galaxy's gas. After a few 100 million years, metallicities might reach 1,000th of solar values. Though still extremely low by modern standards, this level of enrichment significantly affects cooling efficiency and the mass distribution of forming stars. Observing first galaxies remains extraordinarily challenging. They are small, distant, and existed long ago. Light from these galaxies has traveled over 13 billion years to reach Earth, red-shifted by cosmic expansion from ultraviolet into infrared. Only the most powerful telescopes, such as the James Webb Space Telescope, can detect them. Even then, they appear as faint smudges barely distinguishable from background sky, requiring long exposures and sophisticated analysis. The cosmic web structure is visible in first galaxy distributions. Mapping galaxy positions at early times reveals non-random clustering. Galaxies trace filaments, concentrated where filaments intersect and sparse in intervening voids. This pattern reflects the underlying dark matter distribution, which has collapsed preferentially along filaments due to anisotropic gravitational attraction. Galaxies are illuminating the cosmic skeleton, revealing structure invisible to direct observation. First galaxies host nascent supermassive black holes. Some first-generation stars collapse directly into stellar mass black holes. In galaxy centers, where gas densities are highest and dynamical times shortest, these black holes can grow rapidly through gas accretion and black hole mergers. Within a few 100 million years, some will reach thousands or millions of solar masses, becoming the seeds of supermassive black holes that will eventually dominate galaxy centers throughout cosmic history. The epoch of first galaxies is transformative. The universe transitions from simplicity, dominated by dark matter and primordial gas, to complexity filled with stars, galaxies, and chemically enriched gas. Structure forms on all scales simultaneously, from individual stars to galaxy clusters. The cosmic dark ages definitively end, replaced by an era of light and activity. First galaxies herald this new age, the first large-scale, luminous structures to populate the cosmos and begin shaping it into the universe we inhabit today. Some massive stellar cores never explode. When the core is sufficiently massive and collapse sufficiently extreme, not even the powerful supernova shockwave can reverse the implosion. The entire stellar core, sometimes along with overlying layers, falls inward past a point of no return. Gravity becomes so intense that not even light can escape. A black hole is born. A black hole is defined by its event horizon, the boundary separating regions that can communicate with the external universe from regions that cannot. Anything crossing the event horizon is lost forever to outside observers, unable to return or even send signals outward. The horizon's size depends on the black hole's mass. For a 10 solar mass black hole, The horizon radius is approximately 30 kilometers. First generation black holes from massive population 3 stars might have horizons hundreds of kilometers in radius. Beyond the event horizon, physics enters unknown territory. General relativity predicts that in falling matter collapses to a singularity, a point of infinite density where space-time curvature becomes infinite and known physical laws break down. What actually happens at the singularity remains unknown. Quantum gravitational effects not included in general relativity likely become crucial. But whatever occurs there cannot affect the outside universe. The event horizon shields the singularity, making it causally disconnected from external reality. Not every massive star produces a black hole. Stars with initial masses between roughly 8 and 25 solar masses typically produce neutron stars when their cores collapse. The core reaches nuclear density, where neutron degeneracy pressure halts collapse and rebounds to trigger a supernova. But stars exceeding approximately 25 to 40 solar masses produce black holes. Their cores are so massive that not even neutron degeneracy pressure can halt collapse. The core falls through the neutron star phase and continues, collapsing into a black hole. First-generation black holes possess substantial masses. Typical black holes from population stars might range from 10 to 100 solar masses. This significantly exceeds black holes produced by modern stellar populations, which typically range from 3 to 20 solar masses. The higher masses directly reflect the fact that population of 3 stars themselves were more massive. More massive progenitors leave more massive remnants. Black holes grow by accreting surrounding matter. A newborn black hole is embedded in gas, which feels the black hole's gravitational pull. Gas with low angular momentum can fall nearly radially into the black hole, crossing the event horizon and adding to the black hole's mass. However, most gas possesses too much angular momentum for direct infall. Instead, it settles into an accretion disk, orbiting the black hole while gradually spiraling inward as friction and magnetic stresses remove angular momentum. Accretion disks surrounding black holes are among the universe's most luminous objects. As gas spirals inward through the disk, friction heats it to extreme temperatures. The innermost regions, just outside the event horizon, can reach millions or tens of millions of degrees. At such temperatures, the disk emits copious X-rays. A single accreting black hole can outshine entire galaxies of stars, powered by the extraordinarily efficient conversion of gravitational potential energy to radiation as matter falls into the deep gravitational well. Early black holes are seeds for supermassive black holes. Nearly every large galaxy in the modern universe harbors a supermassive black hole at its center, with masses ranging from millions to billions of solar masses. These giants are far too massive to have formed in single stellar collapses. They must have grown over billions of years through sustained gas, accretion, and black hole mergers. Population 3 stellar black holes, though modest initially, are the starting points for this growth. Growing supermassive black holes presents theoretical challenges. Accretion is limited by the Eddington limit, the maximum rate at which matter can accrete without radiation pressure expelling the infalling material. For solar mass black holes, the Eddington limit corresponds to accreting roughly 1/millionth of a solar mass per year. Even at this maximum rate, growing from 10 solar masses to a billion solar masses requires approximately 1 billion years. Yet supermassive black holes exceeding a billion solar masses are observed when the universe is less than 1 billion years old, creating a significant theoretical puzzle. Black hole mergers provide a mechanism for rapid mass growth. When galaxies collide, their central black holes eventually sink to the merged galaxy's center through dynamical friction. The black holes form a binary system, orbiting each other while gradually losing orbital energy to gravitational wave radiation. Eventually, they spiral together and merge in a violent collision that produces intense gravitational waves. This merger instantly doubles or more the black hole's mass. Repeated mergers can grow black holes much faster than accretion alone. Black holes influence their surroundings through powerful feedback. Radiation from an actively accreting black hole heats nearby gas, increasing thermal pressure and potentially driving galactic scale outflows. This feedback can regulate star formation by removing or heating gas that would otherwise form stars. It can also limit the black hole's own growth by expelling potential fuel. Black holes and galaxies co-evolve in a complex feedback relationship where each influences the other's development. Direct collapse provides an alternative black hole formation channel. Under specific conditions, massive gas clouds can collapse directly into black holes without fragmenting into stars first. This requires suppressing cooling to keep gas warm and prevent fragmentation, often achieved by intense ultraviolet radiation from nearby sources that dissociates molecular hydrogen. If conditions are right, clouds containing thousands or tens of thousands of solar masses can collapse directly into intermediate mass black holes, providing a significant head start towards supermassive black hole formation. Favorable conditions for direct collapse are rare. They require pristine gas, lacking molecular hydrogen for efficient cooling, plus strong radiation fields to photodissociate any molecular hydrogen that forms. Such conditions might exist in regions bathed by radiation from nearby galaxies or quasars. Direct collapse is uncommon, but may be essential for explaining the most massive black holes observed in the very early universe. Merging black holes emit gravitational waves that ripple through space-time. As two black holes spiral together, they orbit faster and faster, emitting gravitational waves that carry energy away and cause the orbit to decay. In the final moments before merger, black holes orbit at significant fractions of light speed, producing intense gravitational wave emission. The merger itself generates a brief but powerful burst of gravitational waves propagating outward at light speed. The first black hole mergers occurred hundreds of millions of years after the Big Bang as first galaxies began forming and interacting. These ancient mergers are the earliest gravitational wave sources in cosmic history. Future gravitational wave detectors sensitive to lower frequencies than current instruments may detect these primordial mergers, opening a new observational window into the early universe and black hole formation processes. Black hole properties encode information about their formation history. According to the no-hair theorem, black holes are completely characterized by just three quantities: mass, spin, and electric charge. But these properties carry information. A rapidly spinning black hole likely formed from a rapidly rotating progenitor or from mergers with aligned spins. A slowly spinning black hole might have formed from low rotation progenitors or from multiple mergers with random spin orientations. Studying black hole populations provides insights into formation mechanisms billions of years ago. The distribution of black hole masses offers clues about early stellar populations. If all first stars were extremely massive, all early black holes should have similarly high masses. But if first stars spanned a range of masses, early black holes should show corresponding diversity. Observations combined with theoretical models suggest first stars indeed had a range of masses, though biased toward high values, implying first black holes also spanned a range from 10 to 100 or more solar masses. Some first-generation black holes likely persist to the present day. Black holes that formed early but never accreted much material or merged with others remain small. These primordial black holes, scattered throughout galaxies and intergalactic space, would be extraordinarily difficult to detect since they are not accreting and therefore not luminous. They could reveal themselves through gravitational effects like lensing of background light or subtle perturbations to stellar orbits, but identifying them remains an observational challenge. The era of first black holes overlaps intimately with galaxy formation. Black holes form from first stars, and galaxies form from aggregations of first stars and their environments. By the time galaxies are well established, they likely already host one or more black holes at their centers. These will grow steadily, fed by gas funneled to galaxy centers by mergers and gravitational instabilities. Within a few 100 million years, some will reach millions of solar masses, well on their way to becoming the supermassive black holes dominating galaxy centers today. The seeds are planted, and cosmic time will grow them into giants. "500 million years have elapsed since creation. The universe has transformed beyond recognition from its dark, silent beginning. Millions of galaxies now populate space, each containing millions of stars. The cosmic dark ages have decisively ended, replaced by an era of brilliant starlight and energetic activity. Though evolution is far from complete, the transformation is unmistakable. The universe has become a dynamic, luminous place. Reionization is approaching completion. The vast majority of hydrogen throughout the universe has been stripped of electrons by relentless ultraviolet radiation from stars and early quasars. Individual, ionized bubbles have grown, merged, and coalesced, filling nearly all of space with hot ionized plasma. Only scattered pockets of neutral hydrogen remain, hidden in especially dense clouds, or in the most remote voids far from ionizing sources. The universe has regained the transparency it possessed before recombination, now able to transmit ultraviolet light across cosmic distances. The intergalactic medium has been thoroughly transformed. Gas between galaxies, which constitutes the majority of ordinary matter, has been heated to tens of thousands of degrees by ionizing radiation. Though tenuous with densities of only a few atoms per cubic meter on average, this gas is neither empty nor inert. It forms a warm ionized background, filling cosmic web filaments and the voids between them, serving as the reservoir from which future stellar generations will draw their raw material. Galaxies have become numerous and diverse. At 150 million years, only a handful of small irregular proto-galaxies existed. By 500 million years, millions populate the universe, spanning a wide range of sizes and properties. Some remain small and chaotic, resembling first galaxies. Others have grown larger through mergers and sustained star formation, beginning to develop organized structures. Rotation is increasingly common, with gas and stars settling into disk-like configurations. A few galaxies are already massive enough to host million solar mass black holes at their centers. Heavy elements have spread throughout the cosmos through hundreds of millions of years of supernovae. Each explosion dispersed newly forged elements into surrounding gas. Galactic winds and outflows carry this enriched material across large volumes. The average cosmic metallicity remains very low by modern standards, approximately 1/10,000th of solar abundance, but it is no longer zero. Carbon, oxygen, silicon, and iron exist in detectable quantities, enabling richer chemistry than was possible in the purely primordial universe. Star formation has entered a new phase dominated by population II stars. The first generation of massive metal-free stars has become rare, most having already exploded. Stars now forming are smaller, born from gas enriched by earlier supernovae. These population to second stars have longer lifetimes and lower luminosities than population to 3 stars individually, but they are vastly more numerous. The total cosmic star formation rate is rising toward a peak it will reach several billion years hence. The universe has entered a period of intense stellar birth. The cosmic web is now clearly defined and visible in galaxy distributions. Dark matter's underlying structure, invisible directly, is illuminated by galaxies that trace its architecture. Filaments of galaxies stretch across hundreds of millions of light years, connecting dense nodes where galaxy clusters are assembling. Between these filaments lie vast voids, underdense regions containing few galaxies, where density falls below cosmic average. This magnificent web-like pattern will persist and evolve for billions of years, defining the universe's large-scale structure. Black holes are growing rapidly through accretion and mergers. The first black holes, formed from population third stellar deaths, have been accumulating gas and merging with other black holes for hundreds of millions of years. Some have already reached thousands or millions of solar masses, becoming intermediate mass black holes. These are precursors to supermassive black holes that will eventually dominate galaxy centers. Their growth is accelerated by galaxy mergers that funnel gas towards centers and bring black holes together to merge. Quasars are beginning to appear as some black holes reach supermassive status. A quasar is a galaxy hosting an actively accreting supermassive black hole at its core. The accretion disk surrounding such a black hole is so intensely luminous that it outshines all the galaxy's stars combined. Quasars are among the brightest individual objects in the universe, visible across billions of light years. The first quasars appear around this epoch, powered by black holes that have grown to millions of solar masses through sustained accretion. The cosmic microwave background continues cooling as the universe expands. At 500 million years, its temperature has dropped to approximately 6 degrees above absolute zero. Though still slightly warmer than the intergalactic medium will eventually become, the gap narrows steadily. This ancient radiation provides a faint uniform background glow, filling all space, slowly becoming less significant relative to other energy sources as galaxies and stars produce increasing quantities of optical and infrared light. Gravitational waves from black hole mergers propagate continuously through space-time. Every black hole merger produces a burst of gravitational radiation, carrying information about the black hole's masses and spins. By 500 million years, countless mergers have occurred, creating a stochastic background of gravitational waves pervading the universe. Future detectors sensitive to these low-frequency waves may measure this background, providing a unique probe of early black hole populations and merger rates. The first planetary systems may be forming around second-generation stars. Planets require heavy elements, particularly silicates and metals, to form solid cores and rocky bodies. Hundreds of millions of years of supernovae have now dispersed these elements throughout star-forming regions. Around some population, the second stars, disks of gas and dust, are condensing into planetary embryos. These planets differ from modern solar system worlds, forming from gas with much lower metallicity, but they represent genuine planetary systems. The seeds of future worlds are being sown. The universe is settling into a long period of gradual evolution. The dramatic transformations of the first few 100 million years, ignition of first stars, reionization, formation of first galaxies, are largely complete. What follows is slower and more incremental. Galaxies will continue growing through gas, accretion, and mergers. Star formation will proceed, enriching gas with increasing metallicity. Black holes will grow to supermassive sizes, but the pace of change is more measured. The universe has established patterns that will persist for billions of years. Looking back through cosmic time to this epoch requires observing objects whose light has traveled over 13 billion years. When astronomers study galaxies at 500 million years post-Big Bang, they see them as they existed in the ancient past. This light has been profoundly redshifted by cosmic expansion, with ultraviolet emission stretched into infrared. Observing this epoch demands powerful infrared telescopes capable of detecting extremely faint, distant sources instruments like the James Webb Space Telescope, specifically designed for this purpose. The physics governing this era is well understood through established theory and observation. Models of first star formation, reionization, and early galaxy assembly are grounded in fundamental gravity, thermodynamics, and nuclear physics. Computer simulations running virtual universes forward from initial conditions successfully reproduce many observed properties of early galaxies, providing confidence in theoretical understanding. Yet mysteries remain. Precise details of first stellar masses, the importance of direct collapse black holes, and fine structure of reionization remain active research frontiers. The universe at 500 million years is transitional, balanced between simplicity and complexity. It has evolved from uniformity to structure, from darkness to light, from primordial chemistry to metal enrichment. The coming billions of years will see continued, but less revolutionary change. Galaxies will mature into familiar forms. Stellar populations will diversify. heavy element abundance will rise dramatically. Eventually, conditions will become suitable for complex molecules, planets, and perhaps life itself. Reflecting on the journey from 150 to 500 million years reveals a story of transformation driven by gravity and nuclear fusion. Gravity gathered diffuse matter into dense clouds. Fusion ignited first stars, flooding the universe with light and heavy elements. These elements enabled new stellar types and eventually planetary systems. The universe, once a featureless void, has become a cosmos filled with light, structure, and chemical diversity, universe recognizable as the ancestor of our own. Cosmic dawn has passed, and its first light has illuminated the ancient darkness. The universe has been forever changed by this awakening. The galaxies visible in modern sky, the stars lighting planetary surfaces, the elements composing living things, all trace origins to this epoch. The first 500 million years established patterns and processes that shaped everything that followed, transforming the universe from its simple beginning into the rich, complex system observed today. This is the story of our cosmic heritage, the deep history connecting the Big Bang to the present moment.